Oh, in this first part of Lecture 3, Lecture 3a, we're going to learn more about enthalpy. You may remember from introductory chemistry, we introduced the term there about enthalpy is equal to the heat transferred to or from the system for a constant temperature process. So what we're going to do here is to develop that idea, get a little deeper understanding of that statement. And this is typical of chemistry as you go through the courses. You may learn something on some level, at some introductory level, and then as you take a more advanced course, you realize that, oh, well, I learned it, but now there's even more to learn, and you keep going on that, and eventually you'll get a PhD, and then you presumably know that everything there is to know about a system. So we're going to learn about enthalpy in a little more detail than we talked about in introductory chemistry. All right, let's define enthalpy. Enthalpy will be defined as U plus PV. Now this definition was given in introductory chemistry, but it was sort of pulled out of thin air and no justification was given for it. Let's write enthalpy as U plus PV. Let's write it a different way. U minus PV. And remember minus P dV as related to work? PV work? So what we're doing in defining enthalpy is that we're taking the internal energy, in a sense, subtracting off the PV work. Enthalpy is a state function. And what we're going to show now is that at constant pressure and only PV work, delta H is equal to the heat transferred to the system or from the system at constant pressure and only PV work. All right, so let's start with that. All right, we're going to start with the definition again. Let me switch here. H is enthalpy is defined as U plus PV. Now let's take the differential, look at changes. The infinitesimal change in H will be the infinitesimal change in U, du, plus the infinitesimal change in PV. If you look at calculus of infinitesimals, just like derivatives, derivative of the sum is the sum of the derivatives. The derivative of differentials is the sum of differentials. And then we can go further. This is du. And this would be first times the differential of the second plus the second times the differential of the first. So this is P dV plus V dP. Now we're going to make the assumption that this is a constant pressure process. So we're going to transfer some heat into or out of the system, and that's going to be done under constant pressure. And this is typical what you do in thermodynamics. You start with some general idea and you work it, then you start applying some restrictions and you get some fairly useful equations. So at constant pressure process, this implies that dP is equal to 0. This is constant pressure. P won't change, so dP will be 0. That goes away. So now we have the differential du plus P dV. Now we're going to use the first law of thermodynamics. du is equal to dq plus dw. That's the first law. We're going to apply restriction here. So this is dq minus p dv. That restriction is only, the only kind of work we're doing is pressure volume work. This is only PV work. All right, so constant pressure, only PV work. Let's put this in where to there du. So this is equal to dq minus p dv. So that's, we substituted in there for du, and now we have this term plus p dv. And how convenient. These things cancel out. So this is equal to just dq, and we'll put a p here to indicate that we assumed a constant pressure. And only PV work was done, or could be done. All right, so The enthalpy change, dH, is equal to dQp. Let's integrate this. This is the differential form for enthalpy change at constant pressure. So I'll just write this here, dH is equal to dQp. We're going to integrate this from initial to final states. So integral to dH will be just delta H. And this is a path-dependent integral, so there's no delta there. It really depends upon the path you take. This will just be equal to QP. So there it is. That's the equation you learned in introductory chemistry, and we got that with a little more fundamental understanding of the definition of enthalpy and using calculus, differential calculus here. Okay, let's go back and do a couple of examples. And we just showed that. Let's do a couple examples. Example 1. We have a 250 milliliter sample of water. It's heated from 25 to 60 degrees C in an open container. What is the enthalpy change for this process? And we're given what the specific heat, that's another name for specific heat capacity of water, 4.184 joule per gram per degree C. So when you see specific modifying something, what that means is per mass, so that's why that's per gram there. All right, so let's take a look. Maybe we'll draw a picture here. So here's our initial state. We have 250 milliliters of water, and it's at 25 degrees C, and it's an open container, so we're going to assume there's no storm front coming in to change the atmospheric pressure. So we're going to assume this is constant pressure, atmospheric pressure here. That's our initial state. We're going to take that to the final state, and we're going to do that by putting in some heat, Q. And now we end up with, and we're going to ignore any evaporation, 250 milliliters of water, and this now is at 60 degrees C. So what we want to do is calculate the enthalpy change. Well, this is a constant pressure process. So we can figure out how much heat was added to raise the temperature of water to 60 degrees. That would be QP. And then that would be equal to the enthalpy change because it's a constant pressure process. Well, remember from lecture 2, and if you don't remember, you might review it, that we can calculate Q as mc delta T, where m is the mass of the sample, c is the specific heat capacity, the heat capacity per gram, an intensive variable, and delta T is how much the temperature changed. Well, let's see if we can do this. This is 250 milliliters, which is not a mass, but if we make the assumption that really actually two significant figures, the mass of water is 1 gram per milliliter, so this converts the volume to mass, so we now have mass. The specific heat capacity given in the problem was 4.184 joule per gram per degree C. And delta T, that's the final temperature minus the initial, 60 degrees C minus 25 degrees C. And you plug all this in. I'll put a P here to indicate it's a constant pressure process. This comes out to be 3.7 times 10 to the 4th joule. And that is equal to delta H, because this is the heat putting into the system at constant pressure. So there it is. Let's go do the second example here. The enthalpy of fusion of water is 6.01 at 0C. The enthalpy of vaporization of water at 0C is 45.07 kilojoule per mole. And we're asked to calculate the enthalpy of sublimation of water at 0C. Okay, see if we can do that. Let's write down that information that was given in the problem. It said that the enthalpy of fusion, remember fusion is going from a solid to a liquid. So let's write this down, H2O solid going to H2O liquid. And again, this is at 0 degrees C. And we'll call that delta HF for fusion. That was 6.01 times actually kilojoule. We'll just use that kilojoule. 6.01. Now I want the felt tip pen. Yeah, 6.01 kilojoule per mole. Also given in the problem was the enthalpy of vaporization. Recall, vaporization is going from liquid to a vapor. So the enthalpy change for this process going from a liquid to a vapor, again at 0 degrees C. Delta H, let's call this V for vaporization, is 45.07 kilojoule per mole. And then for sublimation, H2O solid, sublimation, remember, going from a solid directly to a vapor at 0 degrees C. What is this? We'll call this delta HS. All right. Well, let's write down these equations here. These sort of chemical equations. They're not really chemical. They're phase change equations, but we'll call them chemical. H2O, let me just check my notes, make sure I get a, yeah, okay, let's do it this way. H2O solid, going to, yeah, H2O liquid, delta H for this process, call this delta H solid to liquid fusion, delta HF. Then we have the liquid to vapor. Let's write it this way. So liquid going to water vapor. This would be delta H vaporization. What we want is the solid to vapor enthalpy. That's sublimation enthalpy, delta H sublimation. All right. Well, let's, this, by the way, is called a thermodynamic, D-Y-N-A-M-I-C, recording this late at night, thermodynamic cycle. All right, so the cycle means you go around this way. Let's write this this way. So remember from introductory chemistry, if we reverse the direction of reaction, you take the negative of delta H. So going from vapor to liquid, delta H be minus delta H vaporization. Okay, let's go this way. We're now going to make use of the fact that enthalpy is a state function. We're going from a solid to a liquid in two different paths. First, we're going to a solid directly to a liquid. In the second path, we're going from a solid to a vapor, and then vapor to a liquid. It doesn't matter what path we take, the overall enthalpy change will be the same. So because enthalpy is a state function, we can write delta H of fusion, this step, is equal to that step plus that step. Okay, so this would be delta H of sublimation plus, and remember we had to reverse the direction of this and reverse the sign, so this would be minus delta H vaporization. Or in other words, delta H of sublimation will just be delta H of fusion plus delta H of vaporization. Delta H of fusion, 6.01, I'll ignore the units for now, plus 45.07. We add those up, we get 51.08 kilojoule per mole. All right, so that's kind of cool. Thermodynamic cycle. Enthalpy is a state function. We can calculate one leg of this triangle if we know the other two legs. All right, so that's it for enthalpy. We've learned that we can start from our definition and use differential calculus to figure out or to actually derive that equation we learned in introductory chemistry, namely that the enthalpy change is the heat transferred to or from the system in a constant pressure process. And then we did a couple examples. Okay, so that's it for this first part of Lecture 3.